What I'm going to try to do today in this lecture for the audience here and for people streaming at home or watching it on replay is to try and give you some idea about the science of climate change and how it interacts with our need to develop the world and how our population is growing. And I'm going to try and see how these interact and cause the challenges that we face in the 21st century. Now, it's very interesting. Global warming has been around and been known about for the last 35 years. And of course, you see that Business Weekly, Time, The Economist even, all have actually presented the science facts about climate change. However, I see that there are more than one challenge in the 21st century, and we cannot see climate change in isolation. And for me, those challenges are going to be climate change, of course, global poverty, environmental degradation, and of course, global security. And it may sound strange that a climatologist is telling you that climate change is only one of the problems, not the most important one. So, let's look at the state of the world now. 7 million children die needlessly every year. That's the population of London. 700 million people go to bed feeling hungry each night because not enough food. And 1 billion people still do not have access to clean, safe drinking water. That's 1 in 7 people do not have clean water. And I'm going to ask you to worry about climate change in 30 to 50 years' time when the state of the planet is already pretty bad. But I'm going to go further, because this is going to be one of 2 talks, and tomorrow I'll be talking about our other impacts and how we may have even moved into a new geological period called the Anthropocene. And again, scientists have basically looked at planetary boundaries. We've defined boundaries in the natural world that humans are actually pushing at. So as you can see, right in the middle there's climate change. If we go round to the left, we have biosphere integration. We are affecting biodiversity hugely in the world. We have land use changes, freshwater use that we've heard already about in this conference, biogeochemical flows, ocean acidification. We then have aerosols, ozone, and the one I love, top right, novel entities. Because scientists realize that we are producing new organisms all the time, but we do not know what their effect will be on the environment. So climate change is just one of a myriad of effects that we have to manage as stewards of our planet. And I've called this talk the perfect storm. I'd love to take credit for that. Unfortunately, it was a very good dear friend of mine, John Bebbington, who was the chief science advisor to the British government. And in 2009, he realized that the trends in the planet were actually coming together and causing a massive issue. We know that by 2030, in only 14 years' time, the amount of energy the world will need will increase by 50%. Food demand, by the same time, 2030, will also increase by 50%. Not necessarily to feed those most in need, but because of the burgeoning middle classes in many of the rapidly developing countries who require food. And then, of course, to feed both energy and food, you need a lot of water. So there's an increased demand of fresh water of about 30%. And we have to put this in the context of course, rapid development, which is pushing all this, because everybody, quite rightly in the world, wants to have the lifestyle that we all enjoy in the Western world. And of course, on the right, what sometimes is called the elephant in the room, is population growth. And will this actually cause a major problem? And right in the middle of this nexus is climate change. So what is climate change? So climate change is actually just some simple physics, okay? So the sun's energy, most of it is light, comes through the atmosphere. And the atmosphere doesn't see it, it just passes straight through. Apart from a very small amount which is absorbed by ozone, which is great because ozone absorbs high radiation, ultraviolet radiation, which is great because it stops us getting severe skin cancer and causing DNA damage. But for the rest of the energy, just passes through as if the atmosphere is not there. And then it hits the ground. Well, some of it does. A third of it just bounces straight back onto space, gets reflected off white snow, white surfaces, and anything else like clouds that send it back into the atmosphere. 2/3 of it hit the actual ground and changes from light into heat. Any of you who've actually laid out in the sunshine on a beautiful sunny day trying to get a tan, us English try this. Unfortunately, it doesn't happen very often, okay? As you can see, I'm still rather pale despite being in Florida. So again, what happens is you feel hot. And that's because the light energy is hitting your skin and converting to heat. And the energy then is radiated back out. So the energy is then radiated back out from the Earth as heat. And it's lost to space. We know this because otherwise the planet would just keep heating up. So it's in balance. But the key thing is those greenhouse gases capture some of that heat and hold on to it for a little bit and then radiate out of space. Greenhouse gases in the atmosphere in order of importance are water vapor, carbon dioxide, methane, and then you have the nitrous oxides and the CFCs. If you stripped out all of the greenhouse gases, including the water vapor, the temperature of the Earth would drop by 35 degrees. That would mean the average temperature of the tropics would be minus 10 degrees Celsius. So greenhouse gases, really important and good for keeping the planet nice and habitable. And there's a but. We have been burning fossil fuels, changing landscapes, and actually putting CO2 into the atmosphere since the Industrial Revolution. This is the beautiful curve from Mauna Loa, the observatory on Hawaii, where they've been measuring the amount of CO2 in the atmosphere since 1958. This is called the Keeling Curve, and I've always wanted to be a spy in the room when Keeling went to his PhD supervisor and said, I think I should measure CO2. I want to see if it's changing. I want to see if there's a seasonal cycle. And that's great. Can you imagine the supervisor going, so, because he was in California, where do you want to go? And can you imagine the student saying, Hawaii? Of course, the reason he wanted to go to Hawaii was it's a very long distance away from industry, major pollution sources, so he could try and get a clean source. We now have stations both in the Arctic and the Antarctic to actually collaborate and actually compare all this data. So back in 1958, we were down at 315 parts per million of CO2 in the atmosphere. We're now over 400 parts per million. But that doesn't really tell you, that's just a number. What does that actually mean? So if we look at the last 800,000 years, so these are the great ice ages going up and down from the right to the left, both in methane and CO2. And these are measured on ice. So cores from ice from both Antarctica and Greenland are drilled, and the air bubbles, fossilized air trapped in bubbles, is taken out, and we can measure what the past was. And as you can see, it goes up and down with warm and cold periods, but it's always about 200, 250. So by 1958, we were already up to 315 parts per million. And this is what we've done in the last 100 years. So we've increased CO2 by over 40%, and we've doubled the amount of methane in the atmosphere. Okay, so that's the bad news. The good news is that's only half of our pollution. So we produce about 7.5 gigatons of carbon from fossil fuels every year, about 1 gigaton from changes of land use, deforestation, changing land to agriculture from forest or swamp, and that gives you a total of about 8 to 9 gigatons. But the atmosphere only has half of that. The land biosphere, despite us cutting it down, is still absorbing about 2.5 gigatons. The oceans, despite warming up, are still absorbing half of that. So every ton of CO2 we put into the atmosphere, only half of it stays there. And one of the worries that, of course, scientists have is, of course, when will the natural sinks actually slow down and we actually catch up with our own CO2?